Good morning. As George mentioned, I am an assistant professor in the Department of Crop, Soil, and Environmental Science in Auburn University. Auburn University is part of this consortium since the creation of the consortium. For the last 25 minutes, I'm going to share some of the results that we have been getting over the last 3 years evaluating variable rate application of nitrogen on corn in Alabama, and I was able to get some data from George on cotton. I would like to acknowledge my collaborators. As you can see, this is a team effort. It's not one-person job because there are so many variables and so many activities that are behind conducting research of this type. I have a question for you. This is the quiz of today. Okay? Is this the current farming scenario? Is this one? Or is this the future? Okay? Can we predict the future? If we cannot even predict the weather, the daily changes on weather conditions? So we don't know. Nobody knows. I think that if we have this crystal ball, you know, to solve the issues that are coming, not only in the future, but what's going to happen tomorrow. But what is important is that we have the technology. We have so many technologies out there that allows us to be better prepared. And I think the challenge is not only to know that we have technology. The challenge is to use the technology. The technology is not going to do any good to us if we don't know how to use it. Okay? So that's what we are doing, with research at the university. We are trying to figure out how to implement the technology that is out there to your farms, and to learn with you and to learn with the people that develop the technology how to adjust the technology to your operation, because this is not a recipe that there is a technology out there that is going to be able to be used and applicable to every single farm, every single case. Okay? So this technology in terms of nitrogen management allows or should allow us to increase input use efficiency. So when we start talking about precision agriculture in the 80s and early 90s, everybody was talking about spatial variability, okay? And that we were able to adjust the rate or adjust management based on the spatial variability of the field. And I can say that in the early 90s and early 90s, those people were pioneers, okay? But we didn't have all the capabilities. The technology in the early 90s was not available to be able to manage those fields according to the variability that was observed. We didn't have the technology that we have today. Today, we are able to adjust the rate according to the needs of every specific location within a field. We are able to be better prepared in terms of adjusting this operation according to the timing. We know that there are some specific management activities that are very time sensitive. If we don't apply the nitrogen when the plants are needing this nitrogen, we will miss it. So we will probably experience yield losses. And the technology today allows us to keep up good records. And sooner or later, we might have to probably provide these records to environmental agencies. Okay? So when we talk about variable rate application of any input, and Dr. Morari pointed this during his presentation, it makes sense if there is a strong variability within a field. And when we talk about variable rate application of inputs, there are some things that are tangible, like economic benefits and profitability, and there are things that are probably not very tangible. We probably don't see it and are not obvious to us, but they are important and are the environmental consequences or the impacts that we might have on the environment if we follow a practice or a different practice. So in terms of variable rate nitrogen, it makes sense if we have, it makes sense in terms of the money that we'll get into the packet. If there is a strong variability, okay, we will perceive benefits. But there are other benefits that we don't see that are the environmental benefits. So an important component of variable rate nitrogen are the crop sensors. Those sensors that are in the market today allows us to assess these within field changes in growth, within field changes in nitrogen that we can use, and we can measure those changes and then apply the nitrogen according to those changes. So we can apply nitrogen, we can apply plant growth regulators, we can apply the foliant using this type of technology. So we will apply the rate where is needed, when is needed. You might be wondering what are the benefits, and that's why we are here. What are the benefits of this type of technology? This is data from a survey conducted by Purdue University, and it's data from the entire US. It's no data from the Southeast. So on this data, you can see on the bars on this graph represent the yield values. This area of the graph represent corn yield, and this area of the graph represents soybean yields. And you can see that these surveys indicated that in 2001 and 2005, corn farmers that adopted variable rate technology to apply fertilizers, and this is not only nitrogen, it's probably granular fertilizers, they perceive yield increases compared to farmers that didn't adopt variable rate technology for fertilizer application. So I'm going to share with you a little bit of the results of on-farm studies conducted in Alabama and in Georgia evaluating this type of technologies. For the Alabama case, I'm going to show data from 2013, last year data, evaluation that we conducted on 2 different corn fields. We evaluated 4 different treatments. So we evaluated variable rate nitrogen using the Oklahoma prescription, and we applied this nitrogen at the V6 growth stage. Variable rate nitrogen using the same Oklahoma prescription, applying the nitrogen at the V8 growth stage. Over the last 5 years, we have been collecting data to develop our own prescription because we wanted to know if this prescription differed from the Oklahoma prescription. We applied at V8, and then we compared these ones against the uniform application or the farmer rate applied at V6. These maps show the differences in soil electrical conductivity that existed on these 2 fields. One thing that there are 2 important considerations when we talk about variable rate application of nitrogen, either in cotton or in corn, and probably in corn is even more important. One is spatial variability, strong spatial variability. Okay? The other consideration is time of nitrogen application and sensing time. How many corn farmers or how many of you work with corn farmers? Okay. When do you side dress your corn?
We can do it at V6, but normally we have done it, put all our nitrogen out for pre-plant.
Okay. V7. Okay. The question, if we are talking about using the sensors for variable rate application of nitrogen at V6, V4, V7, are the sensors able to capture the variability that is present in the field so you can discriminate or segregate different areas in the field? Okay, or the other question is, are the plants really expressing nitrogen deficiencies or biomass changes within a field at those early growth stages? Because that's the principle behind the variable rate nitrogen application. The sensor is measuring variability in growth and nitrogen. So if the plants are not expressing stress, I mean, the sensors can't do anything. Okay? So what I have on this table are the NDV average, NDVI values for, this is the soil easy map. These are the 3 zones that we delineated on this field based on soil electrical conductivity, shallow and deep. So this is management zone 1, 2, and 3, and this is the NDVI values that we measured at V6. Do you see a lot of differences on NDVI values at V6? There is no much, okay? Let's look at V8, and at V8 you see that this zone 2, that is this zone, okay? The NDVI values were much more different than these 2 zones, and you can see it on this map, okay? And the pattern of NDVI variability is matching the soil electrical conductivity variability. That's what you will look, that's what you will like to see if you are thinking about variable rate application of nitrogen. Okay, so then we apply the nitrogen in a variable rate, and these are the yield results. This is the yield average from the treatments using variable rate nitrogen application using the Oklahoma prescription at V6, V8, the Alabama prescription at V8, and the uniform rate using the farmer's rate, okay? So you see that there are 7 bushels difference between the uniform application of nitrogen compared to the variable rate nitrogen application using Oklahoma prescription at V6. What you will see here, I wanted to show you the data from these 2 treatments, this one and this one, okay? Replication by replication. On replication 4, you see that the variable rate nitrogen treatment, this one, had higher yield than the uniform rate, and it was the same case for replication 6, okay? The other thing that is important to point out is that the variable rate treatment, no matter what replication, was applying less nitrogen than the uniform treatment. When we look at the average values for all those treatments, I want you to look at just only this one, the variable rate nitrogen, Oklahoma V6, and the farmers. Yes, the farmer has higher yield, but on average applied a higher rate of nitrogen per area, and also applied in total, when we look at the total nitrogen that was applied, it was higher. Let's look at this by management zone. We look at the data, and then we see that overall was only on the low EZ zone where the variable rate nitrogen treatment out yield the uniform treatment by the farmer. In the other two zones, the uniform treatment have higher yields than the variable rate nitrogen. And these are the profitability values. You see that only on zone 1 there was an economic benefit, and this is only partial budget. It was only economic benefits on zone 1 using the variable rate nitrogen treatment compared to the control that is the uniform, and we experience or perceive yield losses on zone 2 and zone 3. Okay? Let's look at the other field. And this field, when you look at this map, you see a bunch of colors there. What this means on this soil electrical conductivity map is that in this field there was not a very strong pattern of spatial variability in terms of soil electrical conductivity. It was difficult to segregate very different areas in terms of soil electrical conductivity, and I will say that most of the values of soil EC were within this range. So let's see how this test performed at this field. Again, the same situation when we look at NDVI values. It was difficult to separate or to identify different areas based on NDVI values that early in the growing season at V6, we were able to have a better differentiation in terms of NDVI differences between zone at V8. In this field, again, the uniform treatment by the farmer applying at V6 out yield the variable rate, the two variable rate nitrogen treatments. When we look at replication by replication, looking only at these two treatments, you see that it was only on treatment on replications 1 and 2 where the variable rate nitrogen treatment out yield the farmer's treatment. On the other two replications, the farmer treatment out yield the variable rate nitrogen. But the differences, at least in these two replications, replication 4 and replication 5, were much smaller. When we look at the total nitrogen that was applied on this field, you see that different from the other field, we applied more nitrogen using the variable rate treatment compared to the uniform treatment by the farmer. And I feel like this has a lot to do with the variability. There was not a very strong pattern of spatial variability in this field. That's probably one of the reasons because of those results. When we look at management results by management zones, you see that there were not a lot of yield differences between these two treatments on each one of those zones. But again, we saw that there was, on average, with the variable rate nitrogen treatment, we applied on this field 2 gallons per acre more nitrogen than the uniform rate treatment. In terms of profitability, yes, we were losing money on this field no matter what the zone was when we used the variable rate nitrogen treatment. Okay? And this is corn. Let's change a little bit gears and let's talk about cotton. And these are the results of some on-farm experiments conducted by Dr. Velidis and his team here in Georgia. These are results from 2 different fields. This is again cotton. What you look at this is on field 1, okay? They were able to delineate 3 different zones based on NDVI values. They call the low NDVI zone, the medium NDVI zone, and the high NDVI zone. And this is the amount of the average nitrogen rate that was applied to every one of those zones based on the NDVI values, okay? So when we look at these are the prescriptions. This is an example of the Oklahoma prescription that we're using, okay? And I want you to look at this because this is very important. The Oklahoma prescription works this way. When you have high NDVI values on a field, okay? That means you probably don't need to apply a lot of nitrogen. The plants are not suffering from nitrogen deficiencies. So if you have an NDVI value around 0.7, this prescription is suggesting you have to apply about 40 pounds of nitrogen per acre. But if you have NDVI values, let's say, of 0.65, you probably need to add nitrogen to increase the growth and the yield on those plants. So then you have to apply about 60 pounds of nitrogen per acre. That's the way it works. Okay, so I don't know what happened. Let's see.
That's not that sign, is it?
No.
Let's see.
Okay, I got it. Okay, sorry. So these are the results from this field. From the second field, you see again, these are the NDVI's value. This is the field, okay? This is the field. So they were able to delineate 3 different zones. This one, that is the high NDVI zone, the yellow one, that is the medium zone, and the red one, that is the low NDVI zone. And these are the different rates, average nitrogen rates that were applied on those fields. Let's look at the cost. And this is a table that summarizes the work that they have done applying different inputs on a variable rate. They have different results than we have in corn in Alabama. When they evaluated variable rate application of PGRs, they were able to see economic benefits on 2 fields, okay, by using variable rate application of PGR compared to uniform application of PGR, and these are the dollars per acre. When they were looking at the foliants, they also were able to measure economic benefits by using variable rate application of the foliants. Important economic benefits also when they were looking at variable rate application of nitrogen, and there was much more economic benefits on this field than on that field. So when they said, okay, this farm is about 2,000 acres, and when we account for all these economic benefits of changing rates, either in the foliant or PGRs of nitrogen, that's the amount of dollars that they were able to make on this farm, okay? And this is the last slide of my presentation. This is just focused on side dress nitrogen application on cotton. And I want to point out just this column. There is a lot of information in here, but I want to show you what treatments they were comparing. This is the variable rate nitrogen treatment using the prescription based on the NDVI values by using an algorithm that was developed by Oklahoma State University. This is the treatment VRI-1. This is the uniform treatment, the uniform application of nitrogen, and this is a variable rate nitrogen treatment, but this prescription was based on the soil fertility extension specialist from University of Georgia. So he looked at the NDVI values and he came out with the different rates based on his experience. So let's look at the yield results. So you see that the 2 variable rate nitrogen treatments have higher yield than the control on this field, and in this field was a little bit different. You see that the control have much higher yield than the 2 variable rate nitrogen treatments. In terms of the nitrogen that was applied on field 1, this variable rate nitrogen treatment 1 applied much less nitrogen than the control, and it was the same case for field number 2. That's pretty much what I have for you guys today, and I will be happy to take questions. I don't think we have much time.
No, we have time. We have time for 5 or 6 minutes.
Okay, thank you.
For your NDVI measurements, did you have canopy closure? What was the stage of rows in town?
Who is a farmer, B6 farmer? I just answered, I was just trying to. At V6, most of the times you don't have full canopy closure. He's asking me if at V6 we have full canopy closure when we were collecting the data. At V6, it's hard to have full canopy closure. You have a mix, your NDVI readings are going to be a mix of soil reflectance and canopy reflectance. At V8, you have a pretty good, most of times you have, if no full canopy closure, very close to closure.
What about on cotton?
On cotton, I will let Dr. Veliz to answer.
The question was also about what kind of canopy closure we have when we're doing NDVI measurements. Typically, sidedress cotton is done at the 10 mature leaf stage. So depending on the size of the plants, you may have mostly complete canopies, but typically you don't. But you see tremendous differences in size. You've seen those photographs that we put up there, tremendous differences in size of the plants.
Yes.
On the corn data,
Yes.
what was that? Sandy soil or clay loam or what?
Okay. He's asking what type of, in what type of soil we conducted this test. Loamy sand. Loamy sand.
Next question. I noticed you were using the deep EC data opposed to the shallow EC data.
We delineate, the maps that I show were only, the maps were developed, were created just using the deep, but we use shallow and deep to create the zones. We use both to create the zones just for the purpose of this presentation. I was just showing the soil EC deep data. One more question? Yes.
I'm hearing a lot about spatial variability at the field scale. What are the primary drivers there that's, I feel like we're kind of showing some trends in duplication of EC measurements and NDVI. I just wondered what the primary drivers at the field scale were.
I think that this is, it might change field by field. In my own experience, I feel like soil texture has a lot to do with those changes in spatial variability and also the response of the plants to nitrogen application. And let me give you an example. For the last 5 years, I have conducted a test to be able to come out with the Alabama algorithm. So this test was conducted at 4 different locations in Alabama. And those locations were spread out throughout the state. So I have one site in North Alabama, 2 sites in Central Alabama, 1 site in South Alabama. So if we think this way, I'm covering different weather conditions, but I'm also trying to cover different soil conditions. We collected data, NDVI data at V6, V8, V10 over the last 5 years, and if you think about what happened in terms of weather conditions, climate conditions during these 5 years, those years were different. So what we observe, if we talk about nitrogen and NDVI, just analyzing all this data, and this paper is going to be out in Agronomy Journal in 1 month, is that in the sites, at the sites that have sandy loam texture, and where sites in South Alabama, where we have high temperatures, we were able to discretize or discriminate much better between nitrogen rates early in the growing season, let's say V6. In a location like North Alabama, when we have silt loam soils, the temperatures are much lower, we were able only to see in some years differences between nitrogen rate at V10. So that's what I'm saying, that the recipe, a single recipe is not going to be good for every location.
When y'all say gallons per acre on the natural, what are you using? Is it 32%?
28%.
I'd like to make a comment about this particular slide that Dr. Ortiz showed earlier, and I put up one of your earlier slides. This is the reason why in my Auburn and Dr. Ortiz's service too, the algorithms may be failing us. So when we have parts of the field that we know are highly fertile, highly productive, we already have plants there that are nice and green. The algorithms tend to shut down the amount of nitrogen we put on there. So you look at the result of our graphic, the high EC areas are the ones we would assume to be the most productive. We didn't put as much nitrogen there as we could to maximize the productivity of the part of the field. So the algorithms are not treating this properly. This is why in my art research, we had Dr. Harrison involved, and he was giving us a recommendation to maximize the yield potential of that particular piece of land. So what's happening is that you really have to have fertile land. Relatively higher EC that are very sandy soil, that's a mean acres. You really have fertile land. This is where the algorithms are failing us. This is why in Earth is the primary reason that the overall VRA did not outperform the conventional is that we didn't maximize the yield of this particular piece of land. The farmer's higher rate was able to capture that extra yield. So the algorithms are failing us there. So we have to adjust them. This is where the brains, our brains, consultants, the farmers, not just rely on the algorithms.
Let me just add one more thing, and to complement what George is saying. In my opinion, when we think about variable rate application of let's say nitrogen, we have to consider three components. The variable rate system, I mean the mechanics that allows the sprayer to change the rate, okay? The sensor and the algorithm, okay? So George is saying some of the sensors have still issues, you know, but if you are a farmer, you know your field. The idea and the beauty of the technology, let's talk about sensor, is the sensor allows you to measure the variability in a space, okay? And then let's forget for a minute the algorithm that is in there. Use your own knowledge based on the data that you got from the sensor and take advantage of the variable rate technology, so you change the rate based on the sensor reading, but on top is your knowledge of the field and it's your decision based on those readings.